Lindsay Riley, and this is my artificial blood vessel assignment. So this was some of the research that I found about blood vessels. So the average outer diameter is around 7 millimeters, and the average inner diameter is around 5 millimeters. The resting flow rate was about 2.5 times 10 or 25,000 millimeters cubed per second, and the outside pressure is around 0.007 megapascals. The systolic blood pressure within the blood vessel is 0.16 megapascals. And in order to create a successful blood vessel, aka an artery, the blood vessel needs to be elastic, which means it needs to handle flow that potentially contracts and expands. It also needed to be of a smooth muscle consistency. These are my drawings for the each of the blood vessel lengths. So we have one at 1 millimeter, we have one at 10 millimeters, which is in the middle, and the 100 millimeter, which is on the right side. So these are each of my materials and their costs. So the first one is polyethylene terephthalate, and it is around 56 cents per pound. The second material is polyether ketone, or PEEK, and it's around $10 per pound. And polytetrafluorethylene, which is PTFE, and that is around $8.87 per pound. These are my flow simulation results. So I didn't apply any of the materials to any of them. This was just purely the flow simulation. So I modeled these. I made the outer diameter 7 millimeters, and I made the inner one 5 millimeters. I extruded it to the desired length that it needed to be. And I also made sure to put a lid on it so that the flow simulation was conducted properly. So I put the inlet volume as 25,000 millimeters cubed per second, and I did that for all of them. And then, of course, I made it to its desired length. So for the 1 millimeter vessel, there was a maximum pressure of 0.101639 megapascals. For the 10 millimeter vessel, it was 0.101603 megapascals. And the maximum pressure for the last one, which is the 100 millimeter blood vessel, is 0.102318 megapascals. So from those pressures, I basically ran a new study in order to create the static simulation for these ones, and I input whatever their maximum pressure was. So I input the 1 millimeter maximum pressure into these ones, and I found that the stress and strain for the PEEK, these are the maximum stress and strain, so 1.98 times 10 to the 4th megapascals was the stress, and that was the strain. I also did this for the 10 millimeter one as well, PEEK. So there is the stress and the strain, kind of a bit of outlier going on there. And then I also did it for the 10 millimeter, so it had a 4 times 10 to the 5 megapascals, a strain of 4 to the negative 5 megapascals. And then I also did the same thing with the PTFE. So their stress and strain of this one is a huge outlier compared to what it was last time, compared to the last material. And it had that high of a strain and stress. And PTFE for 10 millimeters, again, it was still a big of an outlier with a stress of 3.9 times 10 to the 5th megapascal and a strain of 2.15 times 10 to the negative 10 megapascal. And again, for the 100 millimeter, 3.92 times 10 to the 5th megapascal, and then 2.1 times 10 to the negative 10 megapascal. And then lastly is the PET results. So it's stress and strain for this one were 1.3 times 10 to the 4th megapascal and 2.15 times 10 to the negative 6 megapascal. And this one, compared to all the other data that I received for the 10 millimeter, this is the best so far. And then here is for the 10 millimeter. Once again, its results are a lot better than the previous two. So 1.7 times 10 to the 5th megapascal for stress, 2.54 times 10 to the negative 5th megapascal. And then lastly, here is the 100 millimeter PET stress and strain stimulation, 2.6 times 10 to the 5th, and then 2.6 times 10 to the negative 5. So in conclusion, PET is the overall best suited to stimulate an artificial blood vessel, and its cost is low with 25.56 cents per pound, and PTFE underperformed, meaning that it is not suited to be an artificial blood vessel because it cannot contract or expand or handle as much as the maximum pressure that it needed to be. And then here are my resources for my assignment. Great, thank you.